Example 5 is now going to get us to practice finding net force. This is another pretty important skill where we've worked with net force back in Unit 1. And we know that net force will have to depend on magnitude and direction. Well, if they're all in the same line, forces can very easily just be added or subtracted depending on their direction. If they're in perpendicular, we need to use the components. So what we want to do is we want to look at this. We have 3 positive point charges, each 2.90 times 10, or 2.90 times 10 to the negative 6 coulombs along a straight line. What we want to do is figure out the net force on B due to A and C. Well, let's think about this for a second. Since they're all equal sizes, then what we need to do is we need to figure out what's the direction each one would push it. Then based on that force, then we could figure out what the final direction would be. So here's the first thing I would do. Look at B, then figure out what direction A would force B. So if B was allowed to move, and ignore C for now, since they're both positive, the force from A would cause B to go in this direction. So we're going to go the electric force from A would cause B to go that way. Since C is also positively charged, and it's also larger, or sorry, not larger, same size, but it's closer, the force from C should be greater and in the opposite direction. So if you were going to draw magnitude and direction on B, if you fixed A and C and B was free to move, B should move a little bit to the left until it's completely balanced and stay stationary, where there is an equilibrium between those two forces. But because it's closer to C, the force from C on B should be greater. So if you wanted to find the net force, because they're in opposite directions, the net force acting on these objects should be the force from C subtract the force from A. I know C will be a bigger force because it's closer, and the fact that they're all equal sizes. Now, if you're ever given a question where you can't figure it out, it doesn't matter. Just when you do the subtraction, you will figure it out by the sign of your answer, which force was bigger. Because if C is bigger, then I'll end up with a positive answer. If A was bigger, then I'd end up with a negative answer, indicating that it moved in the direction of A. So even if you have a tough time, because if they give you different size of charges, different distances, it could be quite difficult to figure out what the net force is. It doesn't matter. As soon as you subtract one from another, you'll know by the sign of your answer which one of those numbers was bigger. Well, I'm going to use the formula here and write this as F net equals K, and I'm going to go QA, QB, or actually I'm going to go, oops, I should be going QB, QC, QB, QC over, I'm going to go the R of BC squared, subtract K, QA, QB over R, A, B squared. And I can put this all into one great big formula. If I wanted to, I could factor out QB and I could factor out K because it's common to all the terms, but I'm just going to substitute it as is. I'm not going to put the units in here because it'll just get too messy. So I'm going to put in 8.99 times 10 to the 9. The charge on B, 2.90 times 10 to the negative 6. The charge on C is the same. So I don't write times 2, but I could write squared, because it's 2.9 times 10 to the negative 6 times 2.9 times 10 to the negative 6. So I can summarize that. And the distance between B and C was 0.0115 squared. And then we're going to subtract 8.99 times 10 to the 9 times, again, the charges of these turn out to be 2.90 times 10 to the negative 6. Again, times 2.90 times 10 to the negative 6 gives you squared, and divide by the distance between A and B, 0.0270 squared. Be very careful when punching this in. Use your brackets and use your squared button. So 8.99 to the exponent 9 times 2.9 to the exponent negative 6 squared divided by 0.0115 squared. Subtract bracket 8.99 to the exponent 9 times 2.90 to the exponent negative 6 squared divide 0.0270 squared. Should give you, I'll have to write this on the next page, 400 F net to 3 sig digs should be 468 newtons. Because it's positive, that means FC was greater, and FC is pointing to the left side of my page, so I'll say to the left in this case. And that's how you answer along a straight line. So if you have multiple charges acting on the object, you need to do a little bit of thinking at the beginning, figure out what directions these forces would be based on the sign, then try to figure out what the magnitudes would be based on the size of the charge and the distance between the charges. Distance is a bigger factor because it's an r squared ratio than compared to the size of the charge. But if there was significantly larger charges, it would play a factor in these. So you need to consider all possible variables in this case. So our answer is, again, to 3 sig digs, 468 newtons to the left.